This is the first mini lecture for section 2.3 of the textbook. It corresponds to section 1.3 of the syllabus. This section is about addition and subtraction. Remember the last couple sections we have basically just been learning how to count. Now we're going to see how addition and subtraction just build on that basic idea of counting. So let's begin by talking about addition. Remember what it means to add. How did you first learn how to do that when you were young? Well, here's a typical example. If I have 3 apples and you have 4 apples, how many do we have altogether? So to answer that, you just put the two groups together and count. You can draw a little Venn diagram if you like. Here's my 3 apples, and here's your 4. 1, 2, 3, 4. Remember how the counting process works. And I put those together into one big group, and then I just count what's there. And it's just the usual counting process. So we've got 1, 2, 3, 4, 5, 6, and 7. So there are 7 altogether. So what this models is 3 plus 4 equals 7. Okay, so addition is based on counting. You just put the groups together and count how many you have in all. And we use that idea to write our formal definition of addition. So we're going to do this in terms of the terminology of set theory that we learned a couple of sections ago. But we're just trying to make precise something that we're already familiar with. If A and B are whole numbers, and big A and big B are disjoint sets, so that the set A has A elements and the set B has B elements, then the sum of A and B is defined as A plus B, which is just the cardinality of the union. You put them together and you count how many there are in all. That is exactly what we just did. And we say that the sets are disjoint just to emphasize that they're not allowed to overlap. So when I say disjoint, what I'm saying is that there's nothing shared. Okay, if there are things shared, you have to be more careful. When we're talking about our apples, if I ask that question about apples, but actually 2 of the apples belong to both of us, it's kind of silly to put the question that way. So we're trying to exclude that from our definition. But on the homework, you'll see a couple examples where you do think about that a little bit. All right, there are 2 basic models for addition when doing things like writing word problems. The first is the set model, which is like we just did. The other is the measurement or number line model, which is kind of a different way of looking at addition. It uses length instead of counting objects. So for example, if Hansel has to walk 3 miles from his house to the lake, then 4 miles from the lake to the village, how far will he walk in all? Okay, so let's draw a number line diagram to illustrate that. We're going to be drawing lots of these. 1, 2, 3, 4, 5, 6, 7. Remember to start your number line at 0. Always do that. And then I'll draw an arrow representing Hansel walking from his house to the lake. And then we draw an arrow representing Hansel walking from the lake to the village. So I start at the 3 and I count 4 more units up, which lands us at the 7. And then here we go. There's the answer. So those are the 2 models for addition. Now we're going to begin talking about some of the properties of addition. So a set of whole numbers is said to be closed under addition It's the word closed. If whenever A and B are in the set, then A plus B is also in the set. For example, an even number plus an even number is always an even number. So the even numbers are closed under addition. Right? That's a fact you learned in grade school. You wouldn't have said this at the time, but what you were really learning is that the set of even numbers is a closed set. Okay, think of it this way. The set is like a little jail, and you're trying to get out of it. If it's closed, there's no way to escape. If it's not closed, then you can get out. Okay, the only tool you have for escaping is adding. So if you can add your way out of the set, then it is not closed. If there's no way to escape from the set by adding, then it is closed. So another example would be the square numbers. The square numbers are numbers like 1, 4, 9, 16, 25, and so on. Are those closed? Well, sometimes the sum is in there, like 9 plus 16 is 25. So, check, that's fine. But, I could do other sums, like for instance, 4 plus 16 is 20, and that's not in the set. Or I could do, 4 plus 9. I get 13, and that's not in the set, so on and so forth. So because a square number plus a square number is not always a square number, it always has to be true to be closed, but this is not always a square number, then the square numbers are not closed under addition. See, I was able to escape. Now, the set of whole numbers altogether is itself closed under addition. That's the closure property of addition. Whenever I add two whole numbers, I always get a whole number. There's always a whole number answer. That's the closure property of addition. Here's one way that often comes up in grade school. Your students will know at some point, even without you telling them, that addition problems always have answers, but subtraction problems do not always have answers. So for instance, 5 minus 8. If I asked the third grader what is 5 minus 8, they would say there's no answer. You can't do that. Well, what they're saying is that the set of whole numbers is not closed under subtraction. Okay, but they are closed under addition because a whole number plus a whole number always has a whole number answer. Okay, next, the commutative property. Given two whole numbers, a and b, it is always true that a plus b is equal to b plus a. That is called the commutative property of addition. So think about this word commutative. It's based on this word commute. Okay, what does it mean to commute? Well, if you're talking about people, it means traveling someplace to go to work, usually. So when you commute, you're moving around. So if you want to talk about A and B commuting, you can imagine them hopping in their little cars and driving past each other. Yeah, that's the way it's described in third grade often. Yeah, these properties are taught in elementary grades nowadays. Maybe you didn't learn them when you were in school. I know that I certainly did not, but you'll probably be teaching them. And this is one way that teachers explain how this works. It's kind of like the numbers are getting in their cars and they're driving past each other. So the fact that you get the same thing either way is what we call the commutative property. And it is something that you kind of have to teach. Even if you don't teach the word, you have to teach the thing itself. Because it might be surprising to you, but your students, it may not be obvious to them that this is always true. It might not be obvious to them that 3 plus 5 is 5 plus 3, that those are always the same. If they're just learning how to add, they've just kind of learn how to count and they're extending counting to adding, this is not going to be obvious to them. They would have to verify it. Okay, so it is something that has to be taught. It's not an obvious property. So let's draw a picture of this 3 plus 5 equals 5 plus 3. And I'm going to use an arrow diagram. Okay, so on top, I'm going to draw 3 plus 5. There's 3 and plus 5. That gets us up to the 8. And then underneath, I'm going to draw 5 plus 3. See, it's a different sum, but it's the same answer. Since they're different sums, you have to draw them differently. But at some point, of course, you'd want your students to just know that the answer would always be the same.